Okay, as a part of higher order elements for one dimensional boundary value problems, in the last class we have seen uh, how to derive shape functions for 3 node element, and also we have seen this derivation of shape functions for higher order elements uh, using two kinds of procedures. One is starting with a polynomial having number of coefficients is equal to number of nodes for the element, and the other way is we derived using Lagrange interpolation formula. So, we can use any of these methods to derive shape functions for higher order elements, and in the last class we have seen how to derive shape functions for a 3 node quadratic element, and also we have seen through examples that the placement of interior node influences the way the shape functions behave, and also we looked at isoparametric mapping concept, and also we have derived the condition for the placement of the interior node in case of a 3 node quadratic element. The distance of the interior node from either of the extreme nodes should not be less than L over 4, where L is length of the element 3 node element. And in today's class we will continue. So, what we will be doing in today's class is we will be deriving element equations using quadratic element for general one dimensional boundary value problem, which we already did earlier using 2 node linear element. So, equations for a quadratic isoparametric finite element are derived for general boundary value problem using exactly the same procedure. Equations for any higher order finite element can be developed, and the problem statement is as follows, for which we are going to develop the element equations. This is a second order differential equation where k, p, q are some known coefficient functions and t is field variable, some field variable, and we need to solve this second order differential equation over the domain x going from, or the lower bound of x is x naught and upper bound of x is xl, and we have derived element equations using 2 node linear element for the same general one dimensional boundary value problem earlier, and the boundary conditions we need to solve this problem subjected to boundary conditions. The boundary conditions are as follows: appropriate boundary conditions for the problem are of the following form. At x is equal to x naught, either you can have essential boundary condition specified, that is t, field variable t is equal to t naught, a specified constant, or a boundary condition which involves derivative, first derivative of the field variable, that is here k naught times derivative of t with respect to x plus alpha naught times t plus beta naught is equal to 0, and this you can easily using the thumb rule that we looked at in the earlier classes, you can easily check that the second boundary condition is natural boundary condition, and here k naught is k evaluated, that is known coefficient k evaluated at x is equal to x naught, and alpha naught beta naught are some specified constants. So, this is either of these boundary conditions can be specified at x is equal to x naught, and let us see the boundary conditions at x is equal to xl. At x is equal to xl, again either essential boundary conditions can be prescribed or a natural boundary condition can be prescribed, where KL is k the unknown coefficient k evaluated at x is equal to xl, and alpha L and beta L are some specified constants. So, we need to develop quadratic isoparametric element equations for general one dimensional boundary value problem, which is stated here, subjected to these boundary conditions. So, now let us look at a typical quadratic element. Both parent element and actual element are shown. In parent element, node 1 is placed at s is equal to minus 1, node 2 is placed at s is equal to 0, node 3 is placed at s is equal to 1, and whereas in the actual element x1, x2 and x3 are the coordinates of nodes 1 and 2, 1, 2, 3, and here for mapping to be valid or for Jacobian to be positive, to remain positive everywhere over the entire element, that is s going from minus 1 to 1, the location of node 2 should satisfy the condition that we derived in the last class, that it should not be closer than L over 4, where L is the total length of the element. It should not be closer than L over 4 to either node 1 or node 3, and the shape functions for parent element also we have derived in the last class, and they are reproduced here. Shape functions for parent element are, these are the shape functions. By substituting s is equal to 1, we can notice that n1 is equal to 1 and n2 n3 are equal to 0. Similarly, similar kind of check can also be made by substituting s is equal to 0 in n2, and also s is equal to minus 1 in n3. So, the trial solution and its derivative with respect to s can be written in this manner, where n1, n2, n3 are put in a matrix, and t1, t2, t3 are put in a vector, and compactly this can be written as n transpose d, where d consists of all the nodal parameters. And now derivative of t with respect, derivative of field variable t with respect to s is given by this one, and now isoparametric mapping, x is equal to sigma ni xi, or here there are 3 nodes. So, isoparametric mapping is x is equal to n1 x1 plus n2 x2 plus n3 x3, substituting n1 n2 n3, which are shape functions of parent element, we get this one, and once we have this relation which is relating x to s, we can easily calculate what is the derivative of d derivative of x with respect to s, that is dx over ds, which is Jacobian, and we require this Jacobian or inverse of Jacobian, because we require to calculate derivative of t with respect to first derivative of field variable with respect to x, which can be written as dt ds times ds dt over ds times ds over dx. So, there ds over dx, to get that we require this Jacobian, which is ds over dx is nothing but 1 over j. So, using this equation, first derivative of field variable with respect to x, first derivative of t with respect to x can be calculated, which can be compactly written as B transpose D, where B is defined as 1 over j times derivative of first derivative of shape functions with respect to s, that is d n1 over ds, d n2 over ds, d n3 over ds. So, now we have the field variable expressed in terms of nodal values or nodal parameters and also its first derivative. So, now we can use the Galerkin criteria to derive the element equations, similar to what we have done in the earlier cases. So, Galerkin criteria, given differential equation, we need to multiply with the weight function, integrate over the problem domain and equate it to 0, and here when we are adopting finite element, weight function is same as shape function. So, multiply the given differential equation with the shape function, integrate over the problem domain, assuming the problem domain is going from x1 to x2, the limits of integration are going to be x1 x2, and since there are 3 nodes here, I takes values 1 2 3, and expanding this, or before doing that we can notice the first term inside the integral is second order derivative is involved in that term. So, we can apply integration by parts, integrate the first term by parts to reduce the order of differentiation. We get this. We have seen this kind of procedure earlier when we are solving problems using Galerkin criteria. So, same procedure you can adopt to do this integration by parts. Now, introducing change of variables, because we need to change the limits of integration from x1 to x2 to -1 to 1. So, introducing change of variables and denoting k times first derivative of t with respect to x evaluated at x3 is k3 t3 prime, and k times first derivative of t with respect to x evaluated at x is equal to x1 is equal to k1 times t1 prime, and then we are going to get the equation after introducing the change of variables and using this notation. The previous equation can be written in this manner, where dx is replaced with jds and rest of the terms follows once we substitute the first derivative of t with respect to x times k evaluated at x1 and x3, substituting the corresponding values, we are going to get this. Now, I takes values 1 2 3. So, expanding this, that is writing all the equations, all 3 equations together in a matrix form, we are going to get this. And please note that here shape function n1 is going to be 1 when it is evaluated at s is equal to -1, and shape function n3 is going to be 1 when it is evaluated at s is equal to 1, and n2 is going to be 0 for s is equal to minus, both for s is equal to minus 1 and s is equal to 1. So, noting all these things, we can further simplify this, and we get this one, where definition of B or B transpose is used to write this the previous equation in a compact manner like this. And from the natural boundary conditions that are given, we can further write k 3 times T 3 prime and k 1 times T 1 prime in terms of alphas and betas, and these are the boundary condition, natural boundary condition that are given, and the element is chosen such a way that the lower limit is x 1 and upper limit is x 3. So, if these are these boundary conditions are specified at nodes 1 and 3 of element, then these equations can be written in this manner: k 1 times T 1 prime is equal to alpha 1 times T 1 minus beta 1. Similarly, k 3 times T 3 prime is equal to alpha 3 T 3 minus beta 3. So, substituting this into the previous equation using these and the known values of shape functions at nodes, the boundary terms can be written in the following manner. And which can be again rearranged, since nodal values T 1 and T 3 are unknown, the boundary terms are arranged into a matrix and vector form as given here. So, this alpha 1 times T 1 plus beta 1 0 minus alpha 3 times T 3 minus beta 3, this vector can be written as minus k alpha times d plus r beta. So, substituting this, the element equations can be written in this manner. And further defining k k, k p and k alpha, the equation can be written as k k plus k p plus k alpha times d is equal to r cube plus r beta, where each of the terms are defined like this. And you can see here in k k you have b transpose and k p n transpose is present. So, we will further simplify and try to figure out what b transpose is and n transpose is, because we require those to perform this integration from minus 1 to 1, and n transpose is defined like this, and b transpose is nothing but derivative of shape functions with respect to x is defined like this, where J Jacobian is obtained once we know the nodal coordinates of all the 3 nodes, and now n transpose is given by this one, and similarly B transpose can be computed, and also we have this k alpha and r beta. So, once we know all these values, we can easily write the element equations for a quadratic element for this particular general one dimensional boundary value problem. And please note that here this k alpha and r beta shows up only if non-zero specified natural boundary conditions are present. Note that k alpha and r beta terms needs to be evaluated only if there is a non-zero specified natural boundary condition at an element n. Suppose if at node 1 natural boundary condition is specified and at node 3 essential boundary condition is specified, then alpha 1 is going to be a non-zero value, whereas alpha 3 is going to be 0. Similarly beta 1 is going to be non-zero value and beta 3 is going to be 0, and vice versa. If natural boundary condition is specified at node 3 and essential boundary condition is specified at node 1, then alpha 1 is going to be 0 and beta 1 is going to be 0, alpha 3 and beta 3 are going to be non-zero values, which we need to figure out from the given natural boundary condition. So, now we have the element equations for a quadratic element for a general one dimensional boundary value problem. So, now we can look in applications of this, and what we will be doing is we will solve the same column buckling problem that we have solved using the element equations corresponding to linear element. So, we will solve the same problem now using quadratic element. If you recall, when we used linear elements, when we discretized the domain using 4 linear elements, we noticed that the solution that we obtained has, or the critical buckling load that we obtained as a solution using 4 linear elements for column buckling problem, we notice that there is about 5% error. Now let us see how can we how much improvement we get using this quadratic element for the same number of nodes for the entire domain. So, here we will be solving the same problem using 2 quadratic elements, compute buckling load for simply supported column shown in figure below. So, we will be using same discretization, or we will be using same number of nodes for discretization. When we are solving this problem using linear elements, we used 5 nodes. So, we will be using 5 nodes here also, except that we will be using 2 quadratic elements, and see how solution accuracy improves. So, before we proceed, just we will briefly review what are the boundary conditions and how this the governing differential equation corresponding to this problem can be brought into the form of a general one dimensional boundary value problem for which we developed the element equations. So, the governing differential equation for this simply supported column buckling problem is a 4th order differential equation subjected to the boundary conditions, and here E is Young's modulus, I is moment of inertia of cross section, W is transverse displacement, and for a column with constant EI, the previous equation can be written in this manner because EI is constant, we can take it out of the integral and we get this equation, and this is the governing differential equation which needs to be satisfied over the entire length of column, that is x going from 0 to L. So now let us look at what are the boundary conditions. Boundary conditions, since we are dealing with simply supported column, transverse displacement at both ends is going to be 0 and also curvature at both ends is equal to 0. So that can be written mathematically like this, and it can be easily verified that the first set of boundary conditions are essential, second set of boundary conditions are natural, because first set of boundary conditions are 0th order equations, second set of boundary conditions are second order equations. But this problem, simply supported column buckling problem, is not directly going to fall under the category of general one dimensional boundary value problem. We need to make some substitution similar to what we did earlier. So problem can be converted into second order form if we define y is equal to second derivative of w with respect to x square, because the general one dimensional boundary value problem that we, for which we derived element equations, is a second order differential equation. Somehow we need to bring this fourth order differential equation into the second order differential equation, so that we can write the element equations for this column buckling problem. So doing this substitution, the given differential equation can be rewritten in this manner, and also boundary conditions gets modified, or this differential equations can also be rearranged and written in this manner, where boundary conditions are also indicated, y is equal to 0 both at x is equal to 0 and x is equal to xl. So now we have the column buckling problem in the same form as general one dimensional boundary value problem. So before we proceed further, we can make a comparison of both equations. Comparing this equation with general form, we see that the corresponding variables we can identify, and once we identify the corresponding variables, we can write the element equations. The following finite element equations for a typical quadratic element can be written by comparing the governing differential equation with general boundary value problem. So that is what we did, and these are going to be the element equations, and where kk and kp and j are defined. So these are the element equations. So once we decide the discretization for a particular problem, and once we have the nodal coordinate values available, we can go to each element and get these quantities kk, kp, from where we can easily write the element equations. So now let us look at the column buckling problem. Two quadratic element discretization for this column buckling problem, which is for which the domain is going from 0 to L. The domain 0 to L is discretized using two quadratic elements, or total 5 nodes, and all nodes are equispaced, and element 1 comprises of nodes 1, 2, 3, element 2 comprises of nodes 3, 4, 5, and there is a mistake, element 2, 2 instead of 2, 1 is printed. So, element 2 comprises of nodes 3, 4, 5, element 1 comprises of nodes 1, 2, 3, and you can notice that for both elements 1 and 2 lengths are same, and also the position of nodes locally is as the same distance from each other. So, element equations for element 1 and element 2 are going to be same, since EI is constant. So, now let us see element equations for element 1, noting down the coordinates of 3 nodes, and length of this element is L over 2, and once we have these coordinates x1, x2, x3, we can easily calculate J Jacobian value. You can see here Jacobian for this nodal spacing, and for this 3 node element is L over 4, which is a constant, and which helps us, or in a way it makes our job easier when we are doing integration, because J is constant, which we will realize, or which you will notice when we are actually trying to integrate to evaluate Kk. Kk by definition is integral minus 1 to 1 b transpose J ds. So, since J is constant, happen to be constant for this particular element, in which the nodes are located at the locations 0, 0.25 L and 0.5 L. So, since J is constant, integration becomes simpler. Substituting b transpose and also J value, this can be further simplified by performing integration. We get Kk as this one. So, now we need to assemble, or we need to compute what is Kp. Kp is integral minus 1 to 1 n transpose J ds. Substituting the values of shape functions, vector of shape functions, we get this. J is again L over 4, and substituting J value and further simplifying by integrating, we get this. So, here these integral or evaluation of this integral becomes simpler in one way, because J is constant. If J is not constant, then the integrand is going to be more complicated. Then sometimes to evaluate these integrals is going to be complicated, where we will be adopting numerical integration techniques, which we will be discussing later. So, these are the element equations for element 1. We obtained Kk and Kp, and now element equations for element 2 are going to be similar, since the nodal spacing is same, and also material properties are constant for both elements. Since J is same as that for element 1, equations for this element are exactly the same as those for element 1. So, we got element equations for both elements, element 1 and element 2. So, now we are ready to assemble the global equations, assembly of global equations. There will be a total of 5 global equations, because there are 5 nodes, each element will contribute to the following equations. Element 1 contribution goes into 1, 2, 3 locations of rows and column locations of global equation system, and element 2 contribution goes into 3, 4, 5 rows and column locations of the global equation system. So, with that understanding, since we already have element equations for element 1 and 2, we can write assembled global equations in this manner. And we see that y1 and y5 correspond to x is equal to 0 and x is equal to L respectively. So, y1 and y5 both are going to be 0. So, these are the boundary conditions. Y1, y5 is equal to 0, because essential boundary conditions for this problem are y evaluated at x is equal to 0 is 0, y evaluated at x is equal to L is 0. So, y1, y5 are 0. So, in the previous global equation system, since y1, y5 are 0, we can eliminate rows and columns corresponding to 1 and 5 locations, and we get reduced equations. Remaining 3 unknowns can be obtained from equations 2, 3, 4, and the reduced equations obtained by eliminating 1 and 5 rows and columns from the global equation system is this one. And here, for further writing, briefly we introduced a notation lambda is equal to PL square over EI, and you can notice that this equation system is for an eigenvalue problem, and for this equation system to have a non-trivial solution, the determinant of the matrix should be equal to 0, and by equating determinant of matrix equal to 0, we get the eigenvalues. Eigenvalues are obtained by setting determinant of coefficient matrix to 0, resulting in the following polynomial, because the equation system is 3 by 3, we are going to get a polynomial of order 3 and which has 3 roots. Solving for the 3 roots of this equation, we get lambda 1, lambda 2, lambda 3, and the lowest eigenvalue corresponds to the first buckling mode, as we have already discussed earlier when we are solving same problem using 2 node linear elements. So, by equating the lowest eigenvalue to the first buckling mode, we can obtain the critical buckling load. So, lambda 1 is equal to 9.944, that will be equated to PL square over EI, and back calculate what is P. We obtain P critical as 9.944 EI over L square, and if we compare this with the theoretical value, which is pi square EI over L square, it matches very well. this value compares very well with theoretical value of pi square ai over L square. Comparing this solution with the one obtained by using linear elements, in the earlier lecture it is clear that fewer quadratic elements are needed for comparable accuracy. The corresponding buckling mode, we obtained buckling eigenvalue. The corresponding buckling mode in the first is the first eigenvector, which can be computed by substituting lambda is equal to 9.944 into the global equations and solving for nodal y values. When we are solving for eigenvectors, we need to arbitrarily set one of the y values to 1 and solve for the other values, similar to the way we did for when we solve the same problem using linear elements. So, following the same procedure, setting y1 is equal to 1 and solving for y3 y2 setting y2 is equal to 0 y2 is equal to 1, solving for y3 and y4, we get the buckling mode shape. So, second and third equations gives y3 and y4, thus the nodal values of buckling mode shape are y1 is equal to 0, which is the essential boundary condition, y2 is arbitrarily equated to 1, and we solve for y3 and y4, which happen to be 1.414 and 1, and y5 is again 0. So, buckling mode shape is given by this nodal values, and the complete buckling shape can be obtained over each element by using element shape functions. Once we get the nodal values, that is y1, y2, y3, y4, y5, we can do interpolation using finite element shape functions and get the complete buckling mode shape. So, for element 1, which is going from x is equal to 0 to x is equal to 0.5 L and s goes from -1 to 1, substituting n1, y1, n2, y2, n3, y3, we get this equation which helps us to plot the mode shape of for element 1, and similarly for element 2 x goes from 0.5 L to L, s goes from -1 to 1, substituting the shape functions n1, y3, n2, y4, n3, y5, we get this equation. So, once we have these two equations which represents how the mode shape is changing over element 1 and element 2, we can plot this and get the mode shape for the entire domain going from 0 to L. So, now we have seen one application of this general one dimensional boundary value problem, which is column buckling problem, and you have noticed that the evaluation of these integrals when we are solving this problem becomes simpler, because j happen to be a constant. If j is not a constant, then the integrand become complicated and we need to evaluate these integrals using some numerical techniques. So, we will be discussing some numerical or one of the numerical technique which is widely used in finite elements, that is Gaussian quadrature for evaluating the integrals. So, that we will be discussing now. So, one dimensional numerical integration, and just I want to highlight the importance of this. This is the column buckling problem that we looked at, and you can notice that the discretization involved 2 elements, and nodes locations of nodes are also shown for both elements 1 and 2, and before we solve for critical buckling load or mode shifts, we require to evaluate for each of the elements these integrals, and for this particular for the problem that we solved, it happened that J is constant. In the column buckling example, nodes are distributed uniformly, resulting in constant Jacobian, and thus it was possible to perform all the necessary integrations without much difficulty. And the problem arises when J is not constant, or when the integrand becomes complicated. When J is not constant, its presence in the denominator makes closed form integration in terms of Kk much more difficult. Therefore, numerical integration is usually employed in isoparametric elements. There are several methods available for evaluating integrals numerically. In finite element literature, the Gauss quadrature is usually performed because it requires fewer function evaluations as compared to other methods for comparable accuracy. So, that is the reason why Gaussian quadrature is so popular in finite element method, or in fact in any other numerical technique like boundary element method. In Gaussian quadrature, the integrand is evaluated at predefined points called Gauss points, and some of these integrand values multiplied by appropriate weight called Gauss weight gives an approximation to the integral. So, for example, if a function f x needs to be integrated from -1 to 1, instead of doing this evaluating this integral in a closed form manner, we can evaluate this function f at some specific locations of x, and some of these values of function evaluated at some locations multiplied by some weights. If we sum it up, we are going to get the integral is going to be approximated by summing the function value evaluated at some specific points multiplied by weight, and only thing we require is to know where to evaluate this function and what is the corresponding weight we need to multiply with. And here xi is the location where we need to evaluate function is called Gauss point, and total number of n is total number of Gauss points, W is weight of Gauss point or Gauss weight, fxi is value of integrand whatever is there inside the integral evaluated at Gauss point. The locations of Gauss points and weights are derived in such a way that n points with n points a polynomial of degree 2n minus 1 is integrated exactly. So, the locations values of Gauss points, that is xi and wi, are derived based on this condition that using n points we can, or when we are deriving this, it automatically follows that if we adopt n points, we can integrate polynomial of degree 2n minus 1 accurately, and the details of this procedure, how to obtain these Gauss points and weights, can be found in textbooks on numerical analysis. And here directly the locations of Gauss points and corresponding weights up to 10 points, 10-point quadrature are given in the table below, and here Gauss points and weights are shown for n is equal to 1, n is equal to n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5. For n is equal to 1, Gauss point is 0 and weight is equal to 2. So, that is not shown in the table, and you can easily read the location or the position at which we need to evaluate the integrand from this table, and you can notice that for both locations and weights a space is there between the numbers, which just gives us freedom, or it is up to the user to decide how many significant digits accuracy is required. Depending on that, he can select the rest of the digits from the table, and here n2 to n5 weights, points and weights are shown, and rest of the points and weights are shown in the next table. n6, n is equal to 6, n is equal to 7, and n is equal to 8, and similarly n is equal to 9 and n is equal to 10. The values of Gauss points and also weights are given, and these values of Gauss points and weights can also be obtained using any of the commercial software like MATLAB. So, in the next class we will be looking at some examples through which we will demonstrate how to evaluate integral using Gauss quadrature, using the values of Gauss points and weights given in this table.